Today, I'm diving into something fascinating with the Einstein's special relativity. First, let's talk about the two main postulates. The first one is the Principle of Relativity. It states that the laws of physics are the same in all inertial frames of reference. In other words, whether you're on a train, moving at a constant speed, or just sitting on a bench, the basic rules of physics don't change. On to the second postulate, that is the constancy of the speed of light. It says that the speed of light in a vacuum is always the same, no matter how fast you're moving or where you are. According to special relativity, time and space are not absolute. They can stretch and shrink depending on your relative motion. This leads to some astonishing effects, like time dilation and length contraction. Einstein's theory also insists that no object with mass can reach the speed of light because it would require infinite energy. But wait a second, the twist here is the insufficiency of these two standard postulates. Einstein's 1905 derivation isn't entirely complete. After establishing the law of the constancy of the speed of light for empty space, Einstein applies this law to situations where space is no longer empty. But for this derivation to apply to physical objects, we need an additional postulate, or a bridging hypothesis. This hypothesis would state that the geometry derived for empty space also applies when space is populated with matter. Here's the crux that such a statement implies: that the introduction of matter and its relative motion have no effect on light beam geometry. This is problematic because Einstein himself rejected the notion that a process like light propagation could be immune to other factors. In 1914, he said, "There can be no doubt that this principle is of far-reaching significance, and yet I cannot believe in its exact validity. It seems to me unbelievable that the course of any process, example that of the propagation of light in a vacuum, could be conceived of as independent of all other events in the world." Including this bridge as a third postulate might have damaged the theory's credibility. Experimental evidence, like the refractive index and the Fizeau effect, suggests that the presence and behavior of matter do influence light propagation, contradicting the theory. Without a bridging hypothesis as a third postulate, the 1905 derivation is open to the criticism that its derived relationships may only apply in vacuo, that is, in the absence of matter. This controversial suggestion is highlighted in the book Space-Time Physics. They propose that the 1905 theory, derived by assuming empty space, might only apply to empty space. A similar suggestion that the reduction of general relativity, geometry to special relativities, flat space-time over small regions may be unphysical, was acknowledged but rejected by Einstein in 1914. He stated, "The equations of the new theory of relativity reduce to those of the original theory in the special case where the GMN can be considered constant, and the sole objection that can be raised against the theory is that the equations we have set up might perhaps be void of any physical content, but no one is likely to think in earnest that this objection is justified in the present case." Einstein revisited this problem in 1919, indicating that it is not settled a priori that a limiting transition of this kind has any possible meaning. A further argument for unphysicality can be gleaned from Einstein's solution to the whole problem under general relativity, where he rejects the physicality of coordinate system relationships in truly empty space. Continuing from where we left off, Einstein's special theory is not the only one that combines a form of light speed constancy with the relativity principle. A notable alternative was proposed by Heinrich Hertz in 1890. Hertz's theory suggested that light could be fully dragged by all objects, providing local constancy of the speed of light for all physical observers. This Hertzian theory illustrates that Einstein's two standard postulates, without a bridging hypothesis, are not sufficient to uniquely arrive at the solution of special relativity. While special relativity is often considered the most minimalist solution, Hertz's theory was logically consistent as well. Einstein himself acknowledged this, stating, "It is on the basis of this hypothesis that Hertz developed an electrodynamics of moving bodies that is free of contradictions." However, Einstein dismissed Hertz's theory due to its poor agreement with the Fizeau experiment results, which involved the behavior of light in a moving medium. Interestingly, special relativity also struggled to reproduce the Fizeau results without introducing additional auxiliary rules to address the different behavior of light in a particulate medium. There are also alternative derivations of special relativity. Historically, Hendrik Lorentz and Henri Poincaré between 1892 and 1905, derived the Lorentz transformation from Maxwell's equations. This was in line with what Poincare called the Principle of Relativity. A more modern example comes from Richard Feynman, who derived the Lorentz transformation from electrodynamics without resorting to the ether concept. Interestingly, George Francis Fitzgerald, in response to the Michelson-Morley experiment, made an argument similar to Einstein's as early as 1889. Fitzgerald proposed that a length contraction was almost the only hypothesis that can reconcile the apparent contradictions. Lorentz independently arrived at similar conclusions and later noted the chief difference being that Einstein simply postulates what we have deduced. Following these early contributions, numerous alternative derivations have been proposed based on various sets of assumptions. For example, Vladimir Ignatowski in 1910 and Philipp Frank and Hermann Rothe in 1911 argued that a formula equivalent to the Lorentz transformation could be derived from the relativity postulate itself, without first postulating the universal light speed. These formulations rely on various assumptions, such as isotropy. The numerical value of the parameter in these transformations can be determined by experiment, much like how the values of the speed of light, c, and the vacuum permittivity are determined in Einstein's original postulates. Ultimately, experiments rule out the validity of the Galilean transformations. When the numerical values in both Einstein's and other approaches are found, these different approaches converge to the same theory.